Okay, so as I've been kind of alluding to, our goal in this next section now is to talk not just about the linear and quadratic functions, but the overarching branch of polynomials. Okay. So polynomials really consists of an entire family of linear, quadratic, then to the power of 3 is cubic, quartic is 4, quintic is 5. Honestly, you could go beyond that. It's kind of ridiculous to do so. The diploma won't require you to go beyond 5, but we could do 6, 7, 8, 9, 10, because once you figure out the pattern, it's very similar. But okay, we'll stop there. One more thought, actually. If linear is to the power of 1, we can actually also go to the power of 0. And I'll talk about that on the slide here as well. So let's do a couple of review slides first. You guys know what a function is? I mean, fancy word for an equation, a graph. I mean, it kind of means a whole bunch of things. I like the words input and output. Just the idea that, like, if you plug in the number 3, it gets you back the number 5. You know, something along those lines. Did I talk with you guys about the idea of like a machine where like you input the 3, you get back a 4? Remember me talking about that before? Another way you can do a function is, does it pass that vertical line test? If you can draw a line straight up and down and it never does like a backtracking, then it's a function. Does that make sense? Okay, moving on. Okay. Here's some verbiage or vocabulary. You guys know the words input is like your x value, and that's the domain. You guys know these words? So domain is x values. Those are what you input into an equation. So if I give you y equals 3x plus 5, the input would be, well, what do you want x to be? X could be 1 or 2 or 3 or 7. So that's your domain. Your output is what you get back from it when you're done. So if I plug in 1 for x, 3 times 1 is 3 plus 5 gives you 8. That's an out. This is an input. That's an output. This is a domain. That's a range. All right. Cool. Moving on. All right. There's a lot of different forms you can write things in. One of the most common forms we'd write a function in is in a factored form. Okay. Let's do a quick activity here. Let's write the equation of this graph right here. This is challenging. It's actually what I made you do a lot of last year. We're going to try to write this equation. Tell me something about its factors. What are its factors? Okay, let's work backwards. What are its roots? Look at this graph. Tell me a root. 4. Okay. 4 is a root. All in agreement? 4 is the root. What is the factor? X minus 4. All right, I have a factor. X minus 4 is 1 of them. Does that make sense? Just by looking at the graph, I know that much. There's another root over here. The root is 0. So what would the factor be? It's kind of challenging. You could write x plus 0 or x minus 0 if you want, but usually just write it as x. Does that make sense? Okay, one more thing though. I have this written here. Regardless of the format, all polynomial functions have what's called a linear coefficient. Or sorry, a leading coefficient. Let me just graph this real quick on a calculator. If I were to graph the function, say bracket x, bracket x minus 4, and say, well, this better be the graph, right? Because, I mean, it meets the characteristics. It's not. Right? What it did is it put an intercept right here at the origin, which is where I wanted this one right here to put an intercept. It put an intercept right there as well due to the x minus 4, but it's the wrong way. You guys remember how to flip a graph upside down? A negative leading coefficient. If we had a negative, like there's usually like a number sitting here. If that was a negative number, it flips the graph upside down. So we should actually find out what negative number that is, because it could be -1 or -2. Do you guys recall this a little bit? So what we would do then is we would say the equation in factored form is going to be like y equals, like, say, a, and a is this leading coefficient. I need to solve for a. Now, if I want to solve for a, I need to know everything else but a. So, I mean, there's already a 4 sitting right here, but there's x's and y's sitting there as well. Do we know any other x's and y's? That's what this point here was for, 2. So based on that point right there, I could plug a 2 here, a 2 here for the x2, and a 2 here for the y2. So let me clean it up. It'll look like this. 2 equals a, the unknown coefficient, times by 2, which is times by 2 minus 4. 2 minus 4, negative 2. 2 times by negative 2, negative 4. How do I get a by itself if there's a negative 4 right there? Well, I divide both sides by negative 4. What is my a value leading coefficient going to be? Perfect, yeah, negative 1/2. Does the negative make sense? Yeah, because the graph's upside down, right? We knew that it should be negative. I didn't know what negative number it would be, but now I know it's negative 1/2. So I'm going to go back now to my original graph here, and before I type in the x and the x minus 4, I'm going to insert a negative, say, 0.5. Does that make sense? And that leading coefficient will then change the graph, make it work upside down. Now if I graph it, and do it properly, looks okay. Let's check the table of values. It goes through 0, 0, supposed to. 2 and 2, supposed to. 4 and 0, looks like we got it. Does that ring a bell? Doing that skill from last year. So that's where I want to start with, is one of the ways that we write something is in factored form, where it usually gets written in like a x plus 3, x minus 2. If this was your equation, I know where the roots are already, right? My roots are going to be at minus 3 and plus 2. But we've only ever worked with quadratics. Now when we work with cubics, well, there's just another one, that's all. Does that make sense? And there's still a leading coefficient as well. There's always going to be a number in front, and that affects the direction of the graph. So we'll talk about that as we get to each one individually. So, okay, that's actually what this next slide here asked for. It said determine the equation of the graph on the previous slide in factored form. So we just did that. That was y equals negative 1/2 x minus 4, was it? But you might also be asked to write something in standard form. Do you remember what standard form means? Foil it out, basically. Right, so if it's something is in standard form, foil it. So like I'd go x times x to give you x squared. And then see how there's a negative 1/2 in front? Well, then make it negative 1/2 x squared. And when you foil the x by the minus 4, it'll give you minus 4x. But then you're timesing it by negative 1/2. So minus 4 and minus 1/2 will give you a plus. And then 4 cut in half gives you 2. So this would be that same equation as this one, only this guy is now in standard form. Makes sense? Look at the standard form equation. What's the constant term? Well, there isn't one. Wow, there is. It's 0, right? Does that make sense back to the graph we had here? What's the y-intercept of this graph? It was 0. That makes sense, right? It kind of pieces together. Able to follow that? And the negative 1/2 coefficient is what made the graph go upside down. So I guess, like I've been saying here, our goal now is to take these skills we've learned, quadratics and linears, extrapolate them to now cubics, quartics, and quintics. So in general then, if something is in like standard form and it's a polynomial, it can be written in this sort of format. A leading coefficient, and then an x that goes to an unknown power, like say x to the 5 or x to the 4. I don't care, but it goes to some sort of power. And then we start decreasing one by one. So if this was x to the 5, see how it's n minus 1? Well, 5 minus 1 means now you'd have some x to the 4s, and some x to the 3s, and some x to the 2s. And you'd keep going down the list until eventually you run out, right? What's the thing you always end with? The constant term, right? Which essentially is x to the 0. When you have an x to the 0, it means you don't have any x's. So like when I wrote this one right here, x squared plus 7x, this is actually 7x to the 1. This minus 3 is really minus 3x to the 0. X to the 0 means don't write any x's. Does that make sense? So write a 3 and then stop. Same thing here. This is an x to the 3, an x to the 2, an x to the 1. We should write x to the 0, but how many x to the 0s did we actually have? We had 0 x to the 0s, right? So therefore our constant term here was 0. This guy right here then is actually polynomial, which confuses kids because you've always been told the word poly refers to more than one. But this is a polynomial because in a way you have 0 x to the 5s, you have 0 x to the 4s. You know where I'm going here? You have 0 x to the 1s, and then you have 5 of no x's. So it is still a polynomial, it's just all of the terms are really nothing terms. Does that make sense? Okay, so let's talk about some basic shapes. You guys should already know linear and quadratic. Okay. Now, I'm going to throw some graphs out here letting you know what the pattern, like what continues, and hopefully you guys can kind of see the pattern. I'm going to highlight a few things. Okay. Here's your linear, a nice straight line graph. Does it have any well, let's use the word vertex for right now. Does it have a vertex? No. Here's a quadratic graph. It does have a vertex. It has one vertex, right? Well, this is what a cubic graph might look like. It has kind of like a wiggle in the middle there. How many vertexes does it have now? Well, now it has 2. A cubic has 2. Well, once you figure out the pattern, this guy right here is a quartic. This would be x to the power of 4. You see how it has 1, 2, 3 turning around spots? This would be an x to the 5 graph. It has 1, 2, 3, 4 turning around spots. We actually changed the name then. We don't call them vertexes anymore. A vertex is actually specifically for quadratics. The word I'm going to use is called turning point. Kind of makes intuitive sense. It's where the graph literally turns around. Does that make sense? So first rule of thumb then is whatever the degree of the function is. You guys remember what a degree is? It's like the biggest power. Whatever the degree is, you're going to have one less turning point. Okay, that's actually not a for sure rule, but we'll go with it for now. It can have up to that many turning points. Well, let's talk about why. Remember on quadratics, when we wrote it in a factored form, if I wrote you like x minus 3 and x plus 2, that's a quadratic form. Just looking at this right here, I know I have an x-intercept at 3 and an x-intercept at minus 2. How in the world do I draw a straight line? That's not a very good straight line. How in the world do I draw a straight line that goes through one of them and yet somehow gets to the other one? You couldn't, right? There's no possible way, which means that it can't be a straight line. It means it's going to have to do some sort of turning around to make it occur. Does that make sense? But what happens if it wasn't quadratic anymore? What happens if it was cubic and you had x plus 3, x minus 2, and you had a third one of these guys here? Well, hopefully this makes logical sense. You'd have to have an intercept here at 2. You'd have to have an intercept at minus 1 and this minus 3. I mean, let's say you even do this to get it through those 2 points there. Well, you got to get back to the 2 there, right? The only way this is going to work is if it flips back around again. Does that logic make sense? Okay. There are exceptions to this rule. Okay. So this is only just we're kind of working our way in. There are some exceptions to this rule. It is possible, actually, for a cubic graph to do this right here. Okay. What's actually happened here is there's a root right here of, like, say, x, let's say, plus 2. Right? Like, let's say this guy is minus 2 right here. Okay. Now, ideally, this guy would have gone low enough to provide a couple of more roots. But you guys remember how in quadratic, sometimes a quadratic doesn't have to go below the axis? And the reason why is because it can't be solved using the quadratic formula. It could end up meaning that the leftover bit here is like, say, something like x squared plus x plus 1,000,000 or 1,000 or something like that. This is something that's not factorable, and so it wasn't able to break into 2 pieces. And since it couldn't break into 2 pieces, I don't actually have those 2 roots there. It ends up, like, ignore this half right here. This little bit right here ends up being a quadratic that never actually gets that low. Does that make sense? So you don't actually have to have roots in all of these cases, but you could. Okay, here's a slide just talking about some of the terminology so that we're using the same words. The main things I need you guys to know are the leading coefficient. It affects the direction of the graph. And the constant term is your y-intercept. The last thing we should talk about then is the degree. the degree kind of gives you a clue about how many roots there might be. If it's a degree of 2, it means there's probably 2 x-intercepts. Doesn't have to be, but there could be. And it means there's probably 1 turning point, because it probably turns around once. Is that logical? Okay, here's a slide just referring to the idea I was just alluding to, though, that you don't have to have roots, though. Right? Remember how a quadratic formula? You could have a quadratic that has 2 roots. You could have a quadratic that has 1 root. It is possible to have a quadratic that doesn't even have roots. So it really depends on its factorability. That's a word. Right? If it can be factored, it has some roots. If not, it actually may not actually cross the axis. So it doesn't have to. So I have the word capable here. The higher the degree of the polynomial, the more x-intercepts the function is capable of having. It doesn't have to have that many, but it has the possibility of it. Let me show you an example. I'm going to draw a quartic graph. It's going to look like this. You kind of pick up that it's quartic because of the fact that it like flips around 1, 2, 3 times. It gives away that it's a quartic. This will be x to the power of 4. But really what ends up happening is this guy right here provides you like an, say, an x plus 1. This guy right here provides you an x minus 2. And then this guy right here, like the last little bit of it wasn't factorable. So it's probably some sort of like quadratic bit that can't be factored. And if we took the time to FOIL this thing to death, hopefully you guys would agree, it would have an x to the 4 at the front though, wouldn't it? Because this x and this x and this x squared would make it to the power of 4. It's just only part of it was factorable. Okay, so my next bunch of slides are basically just walking you through the patterns for how all of the these sort of polynomial graphs work. So here's the first one. This is a constant function graph. What is the degree of this graph? 0. Okay. This would be like the graph of, well, what is the equation of this graph right here? Y equals 2. That's the graph, right? Like literally it's a straight line graph flat across at 2. That makes sense? I mean, if I wanted to be more specific, it's really 2x to the 0. Right? Like there are no x's here. Regardless of whatever you use, y is always 2. I just a flat graph. We rarely use these, but we could. So let's talk about properties. What's the domain? Well, the domain is this symbol here. Do you guys know what that says? Element of the reals. It's a fancy math way of saying every x is valid. Okay. Think of a machine that's supposed to do functions. Okay. And so you give me an input value. Give me a number. No, it's 2. Give me a number. No, it's 2. Give me a number. I don't care. Give me a number. No, it's 2, right? That's literally what this machine does here, is you give me an x number, right? What did you tell me again? You said 7, right? So you said 7. This right here should have been a 7. And then I basically said 0. Now, I don't want any 7s. Get rid of the 7. And I basically said, no, it's a 2 instead. Does that make sense? Regardless of whatever x value you put in, it has to be 2. Right? That's how a constant function will work, is you really just ignore the input. So is there any number that you couldn't tell me? I mean, you could tell me 3 or 7 or 9. Either way, I mean, you can tell me the number, but I'm still going to make it 2 regardless. You get how that goes there? So your range then, the y value, there's only one y value possible. 2. Right? Whatever the number is, that's what this happens to be. Okay, we talk about a few more things here then. This is something that would then have an even degree. You guys know your evens and odds, right? 0, 2, 4, 6, 8, 10, those are even numbers. 1, 3, 5, 7, 9 are your odd numbers. So because this is x to the 0, we consider this to be an even degree. Okay. Will it have x-intercepts? Well, not unless literally the graph is straight across. If the graph was literally like right across this way, and everything was an x-intercept, but this guy will never cross. One of the reasons why is, can I write it with like an x minus 2 like that? Well, no, because there's not even an x. It's literally just like x to the 0. There aren't even any x's. There's no variables in this thing, right? So there's your constant function. Okay, then there's linear functions. This is what you guys did in grade 10. Let's say that it was like the line, the graph, like say y equals Well, this one's y equals x. But I mean, you guys have learned things like, say, y equals 3x plus 1, or y equals minus 2x plus 7. Right? You guys remember doing this at some point? So let's play that same game. Why don't I use this equation right here? What's your
Billy
name?
Potts, can you please come to the office? Billy Potts, please come to the office.
Turner. Turner, right? Yeah. I know. Okay. Give me a number again. 7. Okay. So in this case, 7. Rather than me just straight up saying no, it's 2. How this one works is we'd go 3 times 7, make it 21. Add 1. Now we'd have 22. Does that make sense? Or give me a number again. You're not full. Give me a number. 4, right? So then you'd go 3 times 4 for 12, plus 1, that'll give you 13. Does that make sense? That's your linear type function. Now, as we go through this list right here, are there any x values that you couldn't use? You should be able to use any x value you want, right? If you want to tell me 7 and you want to tell me 12 and you want to tell me 472 million, we can use any of those numbers. They're all valid. And if you look at the graph, it covers all possible y values. Will it eventually equal 3? Yeah. Will it eventually equal negative 4? Yeah. So the domain and range is elements of the reals, but this is now an odd degree because x is now to the power of 1. And these ones always have one x-intercept and y-intercept. It's always going to cross the graph here and there. There's always one of each. So far, so good? Okay, let's keep building them. Quadratics. So this is our focus last year. Quadratics are back to being an even degree. Now, with them being an even degree, the reason for that is that the largest exponent is now a 2. Now, if I play that same game where we do like y equals 2x plus x minus 7, and you give me a number, we can still do that, but here's where the difference is. Are all outputs possible? Or is there some numbers that are just never achievable, right? Because like say down here, there are some output values that you can never achieve, right? Will this graph ever equal negative 5? No, right? So the big change here is that your range is either less than or greater than a number. That number is your vertex number, right? That's the lowest it'll get to, or maybe the highest it'll get to. And in terms of properties, you could either have 0, 1, or 2 x-intercepts. Because you could have the 2 x-intercepts, you could have the 1 x-intercept, you could have no x-intercepts. Does that work? Okay, so that's all review. Let's keep building. Let's try to figure out the patterns. This is cubic. Cubics have a very similar sort of property to them in that they're actually similar to linears. You know how a linear graph kind of went like across the axis like this? Well, cubics actually do the same thing. Cubics start down here in like the low. You guys know your quadrants? 1, 2, 3, 4. This is 1, 2, 3, 4. Okay. Your linears and your cubics, they actually have similar properties in that they go across the map. Does that make sense? The only difference is linear is literally straight, whereas cubic has this little like ability to like make a flip in the middle. It needs that flip in the middle so there can be possibly 1, 2, 3 intercepts. People follow that? So in terms of properties then, every x and every y is valid, and it could have 1, 2, or 3 x-intercepts. Let's show you some examples here. Here is a cubic with 1 x-intercept. See how that works? It has that little flip there, but unfortunately the axis was a little bit too low to catch the next ones, right? You could have 2 x-intercepts where it does this, and it just barely touches. And you could have 3 x-intercepts, which is probably the most typical one that looks like this. But there has to be 1 x-intercept, at least 1 x-intercept, because it's going to go from this quadrant down here up to this quadrant up here. It's going to do that, and so it has to cross this line at least once to get there. That makes sense? So they're, in a way, very similar to linears. Cubics are kind of paired with linears. Well, if cubics are paired with linears, quartics are kind of similar to quadratics. Because it's based on this. It's based on even or odd. Things that are odd are sometimes similar to each other. Things that are even are similar to each other. So here's what a quartic might look like. it has your 4 different x-intercept locations, right? But do you see how there's a whole section down here of the low side of the graph here where there are no values, it'll never reach that low? That's similar to a quadratic. The other thing that's similar to the quadratic is you have your lowest vertex, only now you have like 3 of them, right? You've got this one, and that one. See how there's like a lot of similarities here? So in terms of properties, sure, the domain is still everything. You could tell me 7 and 3 and 9 to plug in as a value, but your range is still lower or greater than wherever the lowest point on the graph is. This one could have 0, 1, 2, 3, or 4 x-intercepts. I mentioned a few slides ago, really all we know is the capacity. We don't actually know how many there will be, but we know how many there could be. For example, here's a graph that would have 4 x-intercepts. That would be quartic. Here is a graph that has 3 x-intercepts. See how there's 1, 2, 3 of them now. Here's a graph where there is 2 x-intercepts. See how like this little vertex here just couldn't quite make it low enough to get there? It is even possible to have a graph with 1 x-intercept. It means that when it comes down, it just barely touches. And so it really only just touches there the one time. And it's even possible to have no x-intercepts, which would look like that maybe. Actually, not like that. Ignore the looks over there. Does that make sense? Well, once you pick up on the pattern, it's just the same going to the next one. I don't have a slide for it, but what do you think quintics will look like? Well, a quintic would be like x to the power of 5. It is going to start down here and end up here. It's going to go across the map. Unlike quadratics and quartics, they like start here and end here, and they do like their flips in the middle. So this is what an even one will do. It'll start up here and end up here. An odd one will start here and finish up there.
Billy Pot, you comes to the office. Billy Pot,
so once you get the hang of it, a quintic is going to have 4 places where it has to turn around, or at least it has up to 4.
So if they're both facing down, it's still even?
Good question. That's actually the next thing I want to talk about then, is the leading coefficient. So I haven't talked about that yet. These are with positive leading coefficients. You know the smiley face and frowny face graphs? These will be like a positive x to the 4 or x to the squared graphs, right? But if you put a negative in front of it, all it does is it takes the same function and flips it upside down. Does that make sense? So yeah, even if it's upside down, that doesn't affect the. What did you ask to say again? The degree. Yeah. Right, does that make sense? So if it starts here and ends here, or if it starts here and ends here, those are even. So the other kind of odd function then, sorry, I'm getting a little messy here, would be what if the graph did that sort of shape to it? That's still an odd graph, except it's an odd graph with a negative leading coefficient. You guys remember slope, right? This just effectively has a negative slope because it's going downhill. That's all. Does that make sense? Okay, so let's do a little matching game here. Without using your calculators, let's see whether we can figure out which one should be which. So let's talk about the first one here. This is a negative 2x squared minus 6x. So we're looking for a quadratic graph. So it means that it needs to have just one turning point probably. It needs to be upside down. And it needs to have an intercept of 0, right? Because there's a plus 0 on the end there. That first one should be, right? That makes sense? That is an upside down quadratic. It's got an intercept of 0. Wait, here we have a cubic graph. Now the cubic graph has a positive leading coefficient, so it's going to need to go in the positive direction ultimately. Now, by virtue of it being a cubic, it could have up to 3 intercepts. It doesn't have to, but it could. But at least it's going to do that little flippy thing, right? See how this guy right up here, the flippy thing's kind of way up high there, but this guy right here is, oh, there. Okay, here's where some of the exceptions start to come in. What I'm giving you right now are like general rules that should cover most situations, but there are some weird exceptions. This guy right here is a quartic graph. It's the power of 4. But it's going to kind of look like a quadratic. And one of the reasons why it looks like a quadratic is because there's no x squareds and there's no x's and there's no constant terms. Usually what happens is as soon as you start throwing in a whole bunch of zeros, even though it's to the power of 4, it usually starts to look like a quadratic instead. And I can actually show you why. If I were to take this guy right here, 4x to the 4 plus 2x to the 3, I can actually factor out a 2x to the 3. And it would leave me to, like, say, 2x plus 1. Does that make sense? Or maybe even though I could factor out 2x to the 3, even though that's allowed, maybe I could just factor out an x to the squared instead, and leave me with like a 2x squared plus x. Yeah, I did that right now. No, this needs to be a 2. There we go. So I'm kind of factoring it out. Okay. Do you see how like the leftover bit right here is quadratic? Because like the leftover bit is quadratic due to so many 0 terms right here, often it will then look quadratic. Brooke, that's the one that you graphed. So even though it is quartic, sometimes quartics might start to look quadratic, just depending on whether you throw a bunch of zeros in. But this one right here is that one right here. Does that make sense? And then for the last one, negative 3x minus 7, hopefully you recognize that's linear. The negative 3 gives it the slope going down like this. The minus 7 is your intercept down here, so that one's lost. That makes sense? So quick summary of the day. What I need for you guys now to start doing, and use these journals by the way, challenge yourself now to start looking at graphs of things that are not linear and quadratic, but try to the power of 3, 4, and 5, and start getting used to what these graphs look like. Okay. Now, if you can, when you guys are making your graphs from now on, can you write down a few more properties? So some of the things I'm going to be looking for you guys to find are, can you find x-intercepts? There could be 1, there could be 2, there could be none, there could be 6. Right? Can you find them? Find me the y-intercept. There will always be one y-intercept. Only one. Always one, only one. The reason why is that if the graph ever like came back and turned around on itself, like say like this, see how now there's 2 y-intercepts? What's wrong with this graph now? It's not a function. Because it fails the vertical line test. So you'll always have, for sure, one y-intercept. Write down the degree. Right, the degree is just the biggest exponent. Write down the domain. Write down the range. And find any turning points. So if I were to go back to like this example I have written on the board here, just on the whiteboard, what I'm going to want you guys to be able to find is then say my x-intercept on this one was at 0.33, 0. My y-intercept was at 0, 1. My degree, what's the degree of that guy? 1. The domain, x element to the reals, range, y element to the reals, turning point. There isn't one. There doesn't have to be a turning point. I mean, especially on a linear, right? A linear doesn't have any reason to turn around. Quadratics do. Cubics do. So try to write down a few more properties, and that's where I want you guys to start, is just explore these new graphs and get a sense of what they look like. Okay. Just so you have an idea of where we're going then. And I already showed a couple of you guys this, just because you did for calculus. Eventually our goal now is we need to be able to factor cubics, quartics, and quintics, which is more challenging. But at least for right now, let's just focus on our graphs. Does that work? Okay, cool. I'll pause the lesson. If you guys want to take a little break, do a couple of practice questions, maybe start looking at your assignments. If I have your form, I guess you can take off at some point though.